really a great pleasure to introduce our second speaker, who is Myles Steiner from NREL. He got his undergraduate degrees from Queen's University in Canada, where he was growing up, and then he got his PhD from Stanford University. Nowadays he is at NREL, and this will be a technical lecture on multijunction concentrator photovoltaics for US energy production. So let us welcome our speaker.
Thank you. Good morning. Please interrupt me with questions if you have any. It's a little dark, so you may have to shout them out. I don't know if I can see with the back, but if it doesn't make sense or is unclear, please shout out a question. I'm going to talk about the CPV industry. It really sits at a happy marriage between the technology of concentrating light and the technology of 3-5 multijunctions. I'll explain why that is. So, you may have seen this graph just by way of introduction. This is a well-known graph from NREL that shows efficiencies of champion cells as a function of year, a whole range of solar technologies, all the way from the organics at the bottom through the concentrating photovoltaics at the top of the chart. And those are the ones we're speaking of. These are really the highest end solar cells that are out there. They're really perfect crystalline systems, almost perfect crystalline systems. We concentrate the light so you get the highest efficiencies possible. Now everybody's in this room because at some level we all feel like there is growth and opportunity in the photovoltaic world. I hope that's what you feel if you're here. This graph just shows PV production in megawatts as a function of the year. This number here is really only 34 gigawatts, and that's large, but that is small in comparison to the total world production, even the total U.S. production of electricity over a terawatt. So there's lots of room for growth in the solar cell industry. The U.S. is at the bottom of this chart right down here. It's gigawatts. And there's plenty of energy in sunlight. Right? This is a map of the U.S., and this little red square here roughly represents the land area that you would need to cover with solar cells to generate the total U.S. consumption of electricity in 1 year. It's not a tiny area, but it's not a huge area either. So, what are the challenges? So, there are many challenges, but one of them is that the sun is not a laser. And there are two reasons why that's true, and I'll start with the first. And it's that the sunlight is not very intense. Right? The solar illumination at the Earth's surface is about 1 kilowatt per square meter. It's not a laser. A laser is very, very, very high energy beam. Right? If it were a high energy beam that was coming from the sun, then we wouldn't have this diffuse energy. We could harness it very, very easily. So we get about 1,000 watts per square meter. We can only convert about 20% at the module level. That's for good modules. And if you want a gigawatt of electricity, it's still less than it's a lot less than a terawatt, but it's still a lot of electricity. That means 5 square kilometers of photovoltaics. So that's a lot of land, that's a lot of material. How do you do this cost effectively? So there's two ways. One is to minimize the cost of the cells. The other is to minimize the area of the cells. Minimizing the cost of the cells is a huge research area for flat plate manufacturers, silicon, cadmium telluride. Basically, people who look at one sun illumination, minimizing the cost of their production is the main driver, or probably the main driver for their technology. But minimizing the area of the cells is also another way of going about it. You take a big cell and you make it 1,000 times smaller, and you use 1,000 times less material, so your costs come down. Now, if you harness that into a system that concentrates the light, then what you end up doing is you shift the cost of the system away from the cells into the balance of systems. So you make the cost of the cells a much, much smaller fraction of the total package. You spend your money on tracking, on optics, on inverters, all kinds of other things that are comparatively less expensive. And if you do this right, you can develop a system that has very, very high efficiency and is low cost. So that's the subject of concentrator photovoltaics. So this is a schematic of a flat plate, right? It sees all of the light hitting it normally over its full area. And here you have a concentrator. So this is, for example, in this schematic it's a lens, but it could also be a mirror. And it has some front aperture that's very large and focuses the light down onto a smaller cell at the bottom. And like I said before, it shifts the major costs of the system from the cell to the optics. And there's a bunch of ways of doing this. You can use a lens, or you can use a mirror. And the choice of which one you use has consequences. The packaging, the heat sinking is a big deal. When you make cells hotter, they operate less effectively. So, if your cell is no longer in good contact with, some big piece of metal or a fan, then it's going to operate at a higher temperature. It's going to be less efficient. And so if it's sitting out here in space above some kind of mirror, that can have engineering consequences. The reliability and the degradation, are important things to consider, and they can change depending on what kind of optic you use. The chromatic aberration, meaning how much the spectrum is distorted from what's originally shining from the sun to what's actually hitting the cell. That can be a very large function of the geometry of the mirror, and so on. Non-uniform illumination. These are all engineering considerations. Here's a schematic of 3 different mirror configurations that have been implemented in the field. This one's a linear trough, where it's sort of a 2-dimensional mirror focusing onto a line of cells. This one's a dish. Some of the pictures that Dustin showed from SolarTAC had technologies that employed some form of this dish. We have a cell sitting in the middle of a big paraboloid, light coming in from all different sides, focusing onto a small cell. Particularly static. These are some systems, again, the pictures that Dustin showed are very similar. This is a set of Fresnel lenses. So small lenses that focus onto a small cell. There's many hundreds of these Fresnel lenses that are arrayed. That's one way of doing it. This is a big reflective dish where you have a very small set of cells right at the focus of the dish. And it's sort of amazing that you have this enormous thing with only a couple cells in the middle. These things arrayed out into a field can generate megawatts. So there are some fundamental limits to concentrator optics. You can define so if you look at the geometry of the system, you have an input optic, and it's got some acceptance angle, right? It can collect light from some area at some angle to normal. It focuses it down onto a solar cell. And based on these 2 angles, you have some geometric considerations that define the concentration. It's given by this formula, which you can derive from geometrical optics. We want everything here. We want high concentration. We want a large entrance angle. We want a non-grazing exit angle. A non-grazing exit angle means that we don't want the light coming in absolutely flat. Otherwise, you're not going to get anything. So you have to keep the cell a little bit away from your optic. Ideally, you would like to collect as much light as possible, but as you expand the entrance angle, you reduce the concentration. So you can't have all these things. You have to trade some of them off. So what kind of trade-offs do you have to make? Well, there's a maximum concentration, and it's defined by the size of the sun. As far as I know, we can't change the size of the sun, nor can we move it closer or further away. So it defines the solid angle. It's about a little over half a degree at whatever distance it is. And so if you apply that formula, the maximum concentration is about 46,000 times. That's pretty high. The solar cells that we work on don't operate anywhere close to that. The solar cells will probably melt. But there are applications, some of the solar towers that operate up at I think tens of thousands of max concentration. This is the maximum theoretical concentration, 46,000. But that's not necessarily practical for a solar cell, because when you concentrate, you have to keep your optic pointed directly at the sun. Right? The difference between flat plate and concentrating is that a flat plate can pick up solar illumination from all angles. Right? It's most efficient when the sun is directly over the cell, and the efficiency falls off. But the efficiency doesn't fall to 0, and so you can pick up energy from your rooftop solar cell in the morning and in the evening, even though the sun is coming in at an angle. That's not true for a concentrator cell. Especially at high concentration, you have to track. But how perfectly can you track? Well, let's suppose you want to have some kind of tolerance. So if you have some wind, or you have a misalignment, or a rabbit comes and bites one of your tracking cords, and now you're a little bit off, you have some tolerance, and even if you're not perfectly pointed, you'll still pick up energy. So if you want a tracking tolerance of a degree, which is actually quite difficult, that lowers your concentration to about 2,000 x. So there are some challenges to using tracking optics. I mentioned one of them, that you have to be pointed right at the sun and track through the day. So if you look at the trackers out of the airports, it's a one-axis tracker. It's a flat plate silicon module with a single-axis tracker, and it tracks east to west. With Concentrator photovoltaics, you need to use a two-axis tracker. So you're tracking east to west, and you're tracking north to south. Okay, it's basically the same kind of trackers that astronomers would use to keep their telescope focused at a star. And you require good pointing accuracy, which increases with the concentration. The previous slide basically showed that. So if you want to operate at 500x, you can get away with some tolerance. If you want to operate at 1000x or 2000x, you need a much more high tolerance system. You need to be more precise. That raises the costs. Clever optical design can increase the acceptance. I'm not going to talk too much about different optical systems, but it's important to remember that even though we're trying to shift the costs away from the cell and onto the optics are not trivial. Could we concentrate the entire sky? So, effectively, could you put some kind of optic on there that would pick up, as much light as a flat plate module would pick up, but concentrated? So technically, yes, you can do it. You pick up direct and indirect light, so not just the light from the sun, but also the diffuse light, the reason the sky is blue. And you wouldn't have to track. But you only get a concentration of about 2, and it depends on the material that you use for the optic. So it's technically possible, but it's not very cost effective. You've reduced your cell area by a factor of 2. That's not a huge reduction in cost. And you've added complexity. You've now added an optic. You have to clean the optic. So it's technically possible, but it's not very cost effective. What is much more cost effective is using multi-junction solar cells. These are very high efficiency. They are a material system that's compatible with high photon flux that generates high electric currents. So, at one sun, you might be generating something like 30 milliamps per square centimeter. So that means if your cell is, square centimeter, you're only generating 30 milliamps. There's not a lot of current. Contacts can carry that very easily. If you concentrate, you might be carrying something like several amps. So you need to have some kind of circuit that is capable of carrying a higher electric current. And the 3.5s are very capable of that. And the cost is less critical than for flat plates. Now, why are multi-junctions interesting? Because once again, the sun is not a laser. It is not monochromatic. If the sun were monochromatic, then you could have a small detector that picked up a very narrow range. It could be very easy to engineer a photodetector that picked up, 870 nanometer light or whatever. Pick your wavelength of choice, and you could engineer it very, very fast. The sun is in fact broadband, and that has implications for the efficiency of the solar cell. So consider here an example of just a putative P on N solar cell with some band gap, let's say silicon. So there are some unavoidable losses that cell will experience. Photons that are below the band gap don't get absorbed at all. That's a total loss of current. And for those photons that are above the band gap, how far above the band gap are they? Well, they have some energy that's above the band gap. That generates an electron-hole pair that initially has the same amount of energy, but within a matter of femtoseconds, those electrons and holes thermalize to the band edge, and they convert at the band edge voltage. So all of that excess energy between the band gap and the actual energy of the photon is lost as heat. It's called a thermalization loss. And you can't avoid either of them. I mean, there are people who are working on what's called hot carrier solar cells to try to extract those electrons before they cool down, but that's sort of a far out technology. So you have a trade-off. If you pick a low energy cell, a low band gap cell, you'll collect a lot of currents because you'll pick up a lot of photons, but you'll convert them at a low voltage, low efficiency. If you pick a high band gap cell, you'll convert all of the electrons or all the photons at a high voltage. You'll have at a high energy, you'll have a high voltage, but you'll have a low current. And there's some optimum in between. And if it's a simple optimization exercise for a given spectrum. For a single junction, the optimum band gap's about 1.4. It's about gallium arsenide, and you can get an efficiency at 1/7, about 33%. But you can do a lot better with a multi-junction. Because what a multi-junction does is it bends the spectrum for different solar cells, and it converts a narrow range of the solar spectrum at a band gap that's tuned for that spectrum. So the high energy light is converted with a high energy cell, the middle energy light is converted with a middle energy cell, and so on. And so you don't have the thermalization loss, right? Does that make sense? At the same time, you pick up a broad range of the spectrum. Yes?
I think each junction would have a different current from the other, right?
Well, it could, and I'll come to that in a second, but for the best engineering, what you want to do is current match them.
Yeah, so how do you do the current matching?
So you could do it two ways. You can choose the band gaps such that for optically thick material, they are current matched. And that's sort of a mathematical algorithm of how to do that, right? So you could, if you want a two-junction cell, you can find mathematically those two band gaps such that the total number of photons that each one absorbs are equivalent. But if you don't have exactly the right band gaps, then you can thin the material.
Thin the material?
You can thin the material, and I'll say more about that in a second. So this is a graph of efficiency versus the number of junctions, and what you see here is that as you add junctions, the efficiency goes up. It's a bit of a diminishing returns above a certain point. This is a theoretical calculation that it doesn't consider some of the practical challenges. Making a 6-junction cell is not easy. Making a 2-junction cell took many, many, many years. Making a 3-junction cell took many more, so on. So this is a slide that shows two very general ways of achieving a multi-junction. In both cases, what you're doing is you're splitting the spectrum. Do you have a question? What you're doing in both cases is you're splitting the spectrum, and you're allowing the photons in the different energy ranges to land on the different cells. The picture on the left shows how you might do that with some kind of optical prism. You would lay out your cells laterally, and then you would use your optical prism, or let's say a set of mirrors with dichroic films, whatever have you. There's a number of implementations of this. So you actually bend the path of the light differently to each of the different cells. This is often called lateral spectrum splitting. There have been some recent experiments that have tried to show this. Nobody has really shown a really cost-effective way of doing it. One of the advantages is that you can, and I'll talk more about that in a minute, but when you grow these cells completely separately, then you relieve your cells of some of the engineering challenges of growing all of them together. But this is probably a more expensive system that might have some niche applications. The more common way of doing it is to stack the cells one on top, either by growing them separately and then stacking them, or by growing them all together, one on top of each other. You start with the highest band gap on top, it absorbs the highest energy light, everything else is transmitted through, and you put the next band gap below that, that absorbs its region of the spectrum, everything below that is transmitted through, and so on. So when it's grown together, it's called a monolithic stack. When it's assembled from separate pieces, we call it a mechanical stack. But in either case, it's the same thing. So that's in theory. Does this work in practice? Yes, it works in practice. These are champion efficiencies for a number of technologies. Crystalline silicon under concentration, crystalline silicon at 1 sun, SIGs, cat telluride. I assume over the next week you'll hear about some of these technologies. I didn't include organic photovoltaics on this. Here's multijunction cells. 42%, 43%. The world record is 43.5%. So that's about 15 percentage points higher than the next bar on the chart. So it does work. You can get much higher efficiencies when you stack the cells into a multijunction. So let's talk about these multijunctions in real world. The commercial state of the art is the gallium medium phosphide gallium arsenide germanium cell. It's a triple junction. It was originally developed for space. It's built on earlier work, which was a 2-junction that was originally developed for space. And for space, they love it. They make it. It's a single panel. There's no concentration at all. It's a little bit of a different set of criteria. But over the past 10 years, the Department of Energy, maybe 15 years, the Department of Energy has been focusing resources on trying to use these for terrestrial applications. So it's been in production from space. The triple junction has been in production since the mid-90s for space, and for terrestrial, probably the last 10 years or so. The efficiency record for this type of cell is 41.6. And despite the fact that there are a number of technologies, some invented by NREL and being developed at different companies that are have higher champion efficiencies and use slightly different technologies that I'll describe, this still remains the state of the art. It's still the cheapest triple junction to produce, and Even though it doesn't have absolutely the highest, to the decimal point, it still remains the workhorse, yes.
So what's the unconcentrated efficiency that the Mars rover is actually using?
Well, let's see, under 1 sun concentration terrestrial, the world record is about 34%. And for the space spectrum, it's probably a little higher, but I don't have it quite.
So mid-30s.
It's mid-30s.
Mars is closer to the sun.
Mars is farther from the sun. But the space spectrum has about 1,360 watts per square meter, so it's a higher energy spectrum. It's tilted toward the UV. So in terms of binning, we start with a germanium cell on the bottom. It's 0.7 eV. And it picks off these bottom 2 bins here. And then this gallium arsenide cell in the middle, 1.4 eV. And then it's topped by a gallium indium phosphide, about equal portions gallium and indium. Now the efficiency depends on the band gap, and this comes back to your question. So this is a model of the total efficiency of a 3-junction device at 500 suns. It's a function of the band gaps, top, middle, bottom. So these loads are supposed to be 3-dimensional contours, and then we've projected onto the 3 planes the 2-dimensional contours at 51 and 52%. There's 2 lobes to the graph because if you look at this plot on the left, there's actually a water absorption dip at about 1,400 nanometers. Depending on whether you put the bottom cell band gap above or below that water gap, you'll get either the high load or the low load. Efficiencies are more or less comparable, but they do point to different technologies. The germanium-based devices all focus on this lower load because the band gap of germanium is down here, it's below the water, above the water dip. So the symbols on this graph represent different champion cells that have been commercialized over the past 10 years or so. The yellow one is this commercialized germanium-based cell that I mentioned on the previous slide, and I'll talk about the other ones in a minute. You can see they're all kind of far from the optimum, and even in efficiency, there's plenty of headroom between the 40% or so efficiencies that we've measured and the theoretical maximum. So part of it is that band gaps are not the sole parameter. There are other considerations to making a good solar cell. You want high absorption, you want high collection. High absorption you get by having direct band gap material, and you want to have as high an absorption coefficient as possible so that you can use as thin a material as possible. So for example, for gallium arsenide, about 4 microns of material will absorb all of the light above its band gap. Anything beyond that, 6 to 10 nanometers, you're wasting space. Gallium indium phosphide has a slightly different absorption coefficient. An optically thick gallium indium phosphide cell is about 3 microns. So if you put gallium indium phosphide on top of gallium arsenide, you'll get some current in the gallium indium phosphide, you'll get some current in the gallium arsenide. They're probably not going to be the same. So if you thin the gallium indium phosphide, right, you're going to sacrifice some of the current in the gallium indium phosphide. In other words, you're making it thinner than its absorption thickness, and so some of the light is not going to be absorbed. And so in that way, what you would do is you would lower the current in the gallium indium phosphide cell, raise the current in the gallium arsenide cell, and you can current match.
So you're actually sacrificing the high current in the high current layer.
Yeah.
So in this way, you are still losing some of the photons that are coming in.
Right, but the broader point is that a 2-junction device with gallium arsenide and gallium indium phosphide is nowhere near the optimal configuration of band gaps. So if you're forced to use those band gaps, for other considerations, I'll come to in a second, then you do what you can to current match, because if you don't current match, your efficiency is going to go down. So the better way is to try to engineer a structure that has exactly the band gaps that you want, and then you can make the cells optically thick and you sacrifice nothing. So the only time you'd have to thin it is if you're, I say the only time, I mean that's pretty much every cell we've ever made is away from optimal. And so then you would thin it in order to make it current match.
Can you do it in parallel, like each layer can absorb different amounts of photons and create different currents, and you just extract the current from different layer in parallel?
Yeah, you can do a spectrum split, like I showed with the prism, or you could make a multi-terminal device. You could put a terminal in the middle, That complicates things.
Okay, so the cost goes up.
The cost, well, the cost probably goes up. The cost almost certainly goes up. The complexity goes up, and the area is not as efficient because you need to put that terminal somewhere. That terminal is going to shadow the bottom cell a little bit. I can draw it out later, but there have been some exploration of using multi-terminal devices. You know, some of the external electronics get more complicated. You probably need 2 inverters instead of 1. Yeah.
So is it that always the high bandgap material determines my overall voltage current?
No, you can have the cell limited by any of the bandgaps.
Okay.
For these germanium-based cells, the germanium is always overdriven. The current in the germanium is usually twice as high. So these are usually top or middle cell. That's a good question. So you want strong photon absorption. You want long carrier diffusion, meaning electron hole pairs that are created at the back of the cell, you need them to diffuse to the junction. If they don't diffuse to the junction, they don't get collected and they're lost. So you can have beautiful absorption, but you're not collecting it. If you have a low mobility, for example, or you have a low lifetime, you have a lot of defects, and you get carrier recombination before it can be collected by the junction. You want good passivation. It's easy to lose electron hole pairs at the front-back interfaces, and so you want what we call passivate, but really it means chemically or with a different material terminate dangling bonds so that you don't get extra recombination. And you want low resistance as well as So, all those considerations are on top of whether you've chosen the band gaps optimally. And, the material quality is probably the main reason why we're not seeing 52% efficient solar cells. We're seeing mid-40s. Not to minimize the efforts that have gone into a 40%. So why is this cell so hard to beat? And part of the reason is that it's lattice-matched. And it's a very nice fluke of nature that germanium and gallium arsenide have almost exactly the same lattice constants. We can grow a direct band gap with gallium indium phosphide with the same lattice constant. By lattice constant, I mean the dimensions of the crystal in plane. So we understand what lattice constant is. These are very, very pure crystalline materials. And if you can grow it lattice match, then you get essentially no dislocations from one material to the other. Those dislocations can wreck your material. So this cell, despite the fact that it's not current matched, and despite the fact that the germanium is indirect, so you need to have it very, very thick, it's very hard to beat. So this is a sketch of trying to illustrate the problem with lattice mismatch. Here you have 2 materials, material 1 and material 2, one on top of each other. And if you count the number of atoms between this vertical line and this vertical line, there's 10 atoms here, there's 11 atoms here. So imagine for a second what happens when you start to grow. You start with material 2, and now you're depositing material 1. So when you have only a monolayer, it strains itself to be lattice matched, right? In this case, that would mean that the material 1 is being stretched, right? So that forces the crystal to store some strain energy. And that can happen for a few monolayers, maybe even for tens of nanometers, but it can only happen for so long before the crystal collapses and relaxes to its strain-free position. When it relaxes, it has to, that relaxation is mediated by the creation of dislocation. So if you look carefully, there's a half plane in material 2 that terminates at a dislocation. Okay, so if you follow these red lines up, there's an extra half plane right here. So that's a dislocation that has mediated the strain relief, but that dislocation itself is essentially a set of dangling bonds. And that is a prime site for recombination, for non-radiant recombination, by which you end up losing electrical pairs.
Is there any mechanical means where you decrease this strain?
Yes. One more slide. Now, if the dislocations lie only in plane, then they're probably not going to be so problematic, but that's not what happens. They end up turning, and they go through your material. They're called threading dislocations, and that's when you really have problems. So when your threading dislocations go through your solar cell material and really through the junction, you really create problems to lose voltage. So what if we abandon the concept of lattice matching and try to engineer a structure where we do change the lattice constants? So this is a schematic. Actually, it's from a presentation that my boss was giving in Washington to try to get us more money. And it's for a 4-junction device, it doesn't really matter. The point is that there are a number of junctions that are grown. So the lateral dimension here is meant to represent the lattice constant. And so a number of junctions are grown at one lattice constant. And then this junction is grown at a larger lattice constant, and this junction is grown at an even larger lattice constant. And these two graded buffers between are a set of steps where what we've done is we very slowly change the lattice constant in a controlled way, 10 steps, 20 steps, maybe we've changed the growth rate. We've done it with material that's transparent, so the light is being transmitted from here to here. But what you try to do is engineer it so that all of the dislocations lie in the interface between each layer. And so that by the time you get to this layer, you have a relaxed structure that is dislocation-free. Okay, so 2 things. It's relaxed, and all the dislocations that had to be created in order to mediate the change in lattice constant from here to here hopefully lie within these interfaces and don't turn themselves into that material. Okay, and that's key. They're called compositionally graded buffers, and there's been an enormous amount of research on them in the last few years, especially for solar cells. There's also other devices that may require this. And the reason you do this is because if you can change the lattice constant, then you can grow a material that has a more favorable band gap, right? Yes?
Since these multi-junction cells are stacked on each other in series,
Yes.
it means that there should be a recombination at the interface between these 2 cells. So it doesn't matter that interface is governed by some kind of
Why is that?
event.
Why is that true?
Because the electrons from the top cell and the holes from the bottom cell should match at the interface between these 2 cells.
So between the 2 cells is a tunnel junction. So we grow the top cell N on P,
Yeah.
and then we grow a P on N tunnel junction, and then you grow the next subcell N on P. So the tunnel junction converts the majority carrier holes in the top cell into majority carrier electrons in the bottom cell, so you don't get that recombination.
So is it kind of parallel stack or
No.
series?
It's completely series connected.
So we are increasing the open circuit voltage.
Yeah.
So there should be a recombination. There should be a recombination of electrons and holes from the top cell to the bottom cell.
I mean, there's going to be some recombination in each of the junctions, sure.
Sure. So it doesn't matter this recombination is on a dislocation free or on a dislocation existing interface.
There's going to be some recombination inevitably. What you would love to have in an ideal world is that be completely radiative. In other words, that the result of that recombination is you emit a photon. Okay? If you don't get radiative recombination, you get non-radiative recombination. You totally lose the electron from the system. And you're going to have some of that regardless. If you have traps, if you have deep level traps, let's say you have oxygen incorporation, it forms a deep level trap. But if you have a high number of dislocations, then on top of whatever else already existed in the material, you've now increased the cross-section for non-radiative recombination. So you make your material worse. So I agree that you can get recombination even without the dislocations, but you're going to get more.
So
And when you do that, you lower your VOC.
So does it matter if these recombination are radiative or non-radiative?
It does.
Why?
It comes from what's called the detailed, well, it's sort of a thermodynamic calculation, but the more radiative recombination, well, the more non-radiative recombination you have, the less thermodynamic potential you have for conversion.
So we'll talk about it later.
Excuse me,
Yes.
just following up on that, why is it that these structural defects actually cause more recombination? Is there like a fundamental, or is it just something starting to use?
No, if you consider them as, I don't know if you've taken a course in quantum mechanics, but if you consider them quantum mechanically, they effectively create a lower energy bound state. So imagine you have some material, and then you have a square potential within that material. So there's going to be some binding energy. And chemically, it happens because you probably have damping bonds of some sort. But from a quantum mechanical point, you have a bound state. Yeah.
So I guess following up on that, if that is a lower energy state, why would those not just get bleached and saturated and then be no problem?
In other words, with light,
Yeah, like why would those trap states not fill up with, free charges and then no longer be?
They might. Some of them might. They are electrical defects, like other electrical defects, but they probably have a much higher cross section. So you would probably need an enormous amount of light to fill them up effectively. Yeah.
So why don't you use amorphous materials to avoid such lattice constant problem? And also, why don't you use the transparent conducting materials replacing those buffers? So in this situation.
So the second question is that they are transparent. The band gap of the gallium phosphide is 1.8 or so, 1.7. So this is in the orientation of the cell. So all of the high energy light is absorbed here, and then the 1.4 energy light is absorbed here. Once you get here, there are no more photons There are no more photons in the system that are 1.8 eV or 1.7 eV. So all of the photons that are passing through pass right through this material. So it is optically transparent to the light that's going through it.
But why don't you use the amorphous materials? So we got constants, lattice constants problem.
So for example, what's an example of an amorphous material?
Like a ITO.
Yeah, so they're not necessarily the same. They don't have the same material quality. They're not you can get much better material quality and higher voltages out of the 3.5s, and it's a material system that allows for all these alloys to be grown at the same lattice constant. It's chemically difficult to integrate some of the amorphous materials into the 3.5s as a matter of growth. So we grow these by MOCVD, metal organic chemical vapor deposition. Sometimes it's called vapor phase epitaxy. There's a bunch of names, but it's very hard to have a system that can grow the 3.5s at the purity that you require and grow the amorphous materials.
Okay.
There are proposals to use other material systems out there.
Oh, just curious, for the that's mismatch and damping loss problem. Just curious whether you try using hydrogen to terminate the damping loss, like when people do in amorphous silicon.
I've seen some reports of passivation on the surfaces using different chemical species. To passivate in the bulk, I'm not sure how you passivate in the bulk of the material.
Chlorine.
So there is hydrogen in the system. Hydrogen is usually a problem. Whatever passivating effects it may have, it usually causes other problems with impurities. So this is, I guess, running a little long, but yeah.
To reduce the lattice-matching, is there any way other than a graded buffer, for example, the pseudo layer or nanostructures?
That's a great question. It's hard to integrate that in a monolithic stack like this, where you're growing the whole thing in one reactor. But yes, if you want to start on a substrate that you've nanostructurally engineered, I don't know if that's a real word, and then grow on top of that a single junction, yeah, you could do that. There's some reports in the literature of that. Okay, so let me move on. Here's a TM. It's clear on my screen. Here's the growth reaction, and what you have is a gallium phosphide graded layer, followed by an indium phosphide material and then gallium arsenide material. This is the solar cell, and this is sort of an intermittent layer. And what you can see here, if you look carefully, is that this is chock full of defects. There's many, many layers in that grade, and we're slowly changing the lattice constant. And it's chock full of defects. There's some defects at the interface, but the material quality of the indium phosphide and the material quality in the gallium arsenide, I'll take my word for it, because you can't see it on this projection. But the material quality is very good. There's very few dislocations that are threading their way through these two materials. So what we've done here is we've engineered a grade that changes the lattice constant and achieves our aims. It relieves the strain, and it does so keeping the dislocations within the layers of the compositionally graded buffer and not in the active material. So there's been progress made on these germanium-based cells. This is the standard one. And here's sort of two manifestations of a lattice mismatch, both on germanium, but now we put in a grade and changed the top two subcell band gaps. Instead of 1.4 and 1.85, we've lowered them here a little bit and here considerably more. And these two cells represent the green and the pink purplish dots on this graph. They're getting closer to the optimum of that bottom lobe. You don't see you don't really see any increase in efficiency, but you don't see a decrease either, and that's important. It means that we've managed to, at least at this level of research, achieve comparable efficiency with a more optimal band gap, and it creates a platform for further improvements. And if these efficiencies were down in the 30s, I would say that the lattice mismatch is effectively not working well. But what you can see from these results is that it is working well. So what we did at NREL is try to move beyond the germanium-based cell, and we developed what's called the inverted metamorphic multijunction cell. It's a bit of a mouthful, but we abbreviated to the IMM. And it's probably the best platform for achieving the optimum band gaps. And it has the following advantages. You grow the device upside down. You grow the top cells first, followed by the bottom cells. And if the top cells are lattice matched, and they are, what that means is that the most energy productive element of your cell is being grown with the highest material quality. So whereas in the germanium-based cells, the dislocations are formed first, and then you grow these really high-quality top cells. Here you do the opposite. So you have really high-quality material in the most important of the subcells, and you may sacrifice some material quality in this cell, but it's not as important. So what we do is we grow it upside down on the substrate, and then in processing, you flip it over, you bond it to some handle, silicon, or whatever you want. You can bond it to glass, you can bond it to something that was flexible. Then we etch off the substrate, and then you shine light from the top. So this is the final schematic of this cell. It's very thin. This is maybe 10 microns. So 10 microns can easily be conformed to a flexible substrate. The space people love this because you've now eliminated the entire weight of the substrate. Just a note about space is that they have a different set of specs. What they're really interested in is efficiency per weight. And so they get rid of the weight of the germanium. They've reduced their launch costs. And so that was a junction with one metamorphic junction. That was the blue one. And in fact, we've gone further. We've made cells with two metamorphic junctions. So here, all three of the band gaps have been reduced from their original one. So there's you grow it here, start down this way, and then flip it over. So here's 0.9 EV, 1.34 EV, 1.83 EV. That's at this red point, which is at the bottom of that lobe. It's getting even closer. Again, the efficiencies aren't skyrocketing, but this is a platform for the engineering of any band gap you want, right? Because you can change this band gap, you can change this band gap, and if you put a grade at the very beginning, you can change the first band gap. So if you look at a TEM version of that one, what we did is we took a fib, a focused ion beam, cut out a small section, did a cross-sectional image, and then TEM. So here's the substrate, here's the top, middle, bottom cells, and then, again, it doesn't come out so well in projection, but there's a graded layer here and a graded layer here. And if you look at the TEM dark field images, those two graded layers are chock full of dislocations. But the materials of the solar cells here, here, and here are actually very, very clean. And if you look at cathodoluminescence, essentially maps out dislocations. There's essentially none in the field of view on the high-quality top cell. There's about 10 to the 5, which is a very low number, in the middle cell, and about 10 to the 6 in the bottom cell. This is sort of what we aim for in terms of dislocation density. Much more than that, you start to decrease your VOC, your own circuit voltage.
Scale bar on the upper right. We're not seeing atoms, are we?
No, this is 40 microns by 40 microns. 40 microns by 40 microns. So 16 dots is 10 to the 6. So here you have 2 dots, here you have 32 dots. So this is a graph of our best result at NREL to date. This is efficiency versus concentration. This is a device with one metamorphic junction, so it's got a 1 EV bottom cell. You can see, we're pretty proud of this result. It's 42.6% at 320 suns. And it maintained its efficiency all the way out to almost 41% at over 1,000 suns. And there's a lot of work on, minimizing this rollover. Obviously increasing the whole magnitude of the curve, shifting it upward to begin with, but also decreasing that rollover. If you can maintain a high efficiency at 1,000 suns, you use half the material that you would need if you were at 500 suns. So again, it's a cost leverage in terms of the system.
Is it the waste heat that's causing that rollover?
It's probably not so much heat as, well, it's resistive loss. Yeah, it's resistive loss. I mean, you have the emitter of the cell has some resistance. You have a lot of current going through the wiring. That's the dominant.
Excuse me.
Yes.
Just another question on this. So do these things degrade at different sort of time scales for different sun concentrations?
That's a great question, and there's not a lot of evidence. We're sort of trying to develop a sense of the reliability. I'm not sure if you mean do the different parts of the cell degrade or do the different cells degrade?
Just at different sun concentrations, do they degrade in a different way?
I mean, my guess is that they would degrade faster at higher intensity, but I don't actually have a lot of empirical evidence for that. Part of it is that it's hard to acquire that evidence because you develop an optical system to put outside. It's got a fixed geometrical concentration. It's not hard, So to actually go about installing a system that was at 100x, then 400x, then 1000x, you really need to develop 3 totally different systems. We've done some laboratory-based stuff with lasers on single junctions. They don't show a lot of degradation rate variability between intensities, but it's small statistics. My instinct is that at higher concentration you'll have more degradation, but it's not entirely obvious that that's the dominant mechanism for degradation. It might be that the humidity is more. Yeah.
Does each subset have a different performance than the other under different sun concentration? I mean, is there an optimum sun concentration for each subset?
To first order, I think the answer is no. You design the whole system for a particular concentration, and then you optimize. You pick a concentration that you want to operate at, and that may be informed by the cells, but also the optics and the cost of what's available. And then you design the entire system for that concentration. So you would optimize the middle junction for 500x, you would optimize the top junction for 500x. I'm sure there are second order corrections to that, but it's a first order no.
Just out of curiosity, when you're saying that you really want to minimize the area of these cells because they're so expensive, like how much per square inch are we talking for these kind of things?
These are something like 50,000 per square meter.
Okay.
Something like that. They're pretty expensive. 50,000 per square meter is $5 per square centimeter.
Yeah.
That's a lot higher than silicon. And there's a lot of work on reducing that. That's a ballpark number, but there's a lot of work on reducing that cost. And some of it is reduced by being able to recycle the substrate. So in our inverted technology, you can remove the substrate. If you can remove it and reuse it, that's a driver for lower costs. If you could make those grades thinner, those are all drivers for lower cost. So I wanted to sort of end with this montage of champion cell efficiencies. This is a graph of bandgap versus lattice constant, and the white lines sort of show the alloy system between gallium arsenide and arsenide and gallium phosphide and so on. And there's some efficiency vectors here. So this is Spectralab's 41.6 result with Lattice-Matching germanium is the first one I showed you. And then there's the Lattice-Mismatch ones on germanium, where the top 2 junctions have been pushed to lower bandgaps. And it has a comparable efficiency. Then NREL and more recently Sharp Solar have, and this has been commercialized by MCOR, and this is sort of the main inverted metamorphic multijunction cell that's been commercialized. It has a lattice-matched top and middle junctions, but a mismatched bottom junction, and right now Sharp has this world record of 43.5. It's a bit of a parlor game, these world records. These are all within uncertainty of each other. This past year, Solar Junction company in California actually came up with also a 43.5% result that was completely lattice-matched. And they went sort of a slightly different way than what we've been talking about, but they used this nitride-based gallium arsenide nitride material. It's probably a pretty crappy material, but they do it sufficiently well that it doesn't offset all the gains in the rest of the cell. They got this beautiful result. And then there's another result from NREL where we changed the lattice constant of 2 of the junctions, so a 2 metamorphic junction. So this is sort of a snapshot of some of the champion cells in the industry or in research. I think the take-home point from this is that there's several take-home points. One is that there's still headroom between the best efficiencies and the theoretical maximum. Number 2, there's a whole bunch of different technologies here. Some are germanium-based, some are inverted, some are lattice-matched, some are lattice-mismatched. they're all getting comparable efficiencies, which is more to trying to tell you that they're all drivers of high efficiency, and what really distinguishes the choices between one or the other are sort of the cost-benefit analysis, right? You know, your growth time is lower, your material costs are higher in one, lower in the other. The available concentration that you want to use is different. But you know, at the same time, there's been a clear progress in efficiency. As you can see from this graph, once again, I showed this in the beginning. So all of the cells we've been discussing all line on this line. This line is not saturating. And what's going to, you know, two things are going to continue to push this line up. Improvements in efficiency, improvements in material quality and architecture of cells, and higher number of junctions. So, you know, my group at NREL and several of the companies that I've alluded to all have research programs looking at 4 junctions and then down the road 5 and 6 junctions. You know, the economics of some of these higher junction devices is not completely clear. There's a diminishing returns at some point. But most people tend to agree that a 4-junction cell is more cost beneficial than a 3-junction cell, and that's where the research is heading. So I look forward to adding points to this graph over the next few years. Thank you for your attention.
Do we have questions? Yes, please.
I'm curious to know, is there any current-driven diffusion of atoms between the interfaces?
Probably. There's a lot of reliability studies from the LED industry, especially, you know, the LEDs operate under very, very high currents. There's some evidence for atomic migration. The currents that we see here are lower. That's not to say that they're so low. I don't think that it's a big problem, but you know, from a scientific point of view, it's probably something that exists in our cells.
If you showed a plot of efficiency versus concentration for these triple junction devices, what's the reason for the roll-off you saw at extremely high concentrations above, say, 600 sinus?
Yeah. Let me go with that. This one here. Yeah. So there's several reasons. The main reason is series resistance. So you have series resistance throughout the cell. You have ohmic. You have tunnel junctions between the subcells that have some ohmic resistance, and you have spreading resistance at the front. So your grid covers the front of the cell. You have to get these high currents from the semiconductor into the external circuit. So you're going to get I²R losses. You have some spreading resistance through the semiconductor itself. At low concentration, the spreading resistance, or all the resistances, are somewhere between irrelevant and and small. But at high enough currents, they start to dominate. And to the extent that you can eliminate them, you can eliminate that rollover.
Okay, so what's the driver? Is the resistance in the cell or the resistance at the tunnel junction and at the contact?
So it's probably the top of the cell. The tunnel junctions are pretty good. If you look at the slope of the tunnel junction at 0 volts or near 0 volts, it's pretty high. So the resistance of the tunnel junction is probably not the main driver. The top of the semiconductor, the emitter of the top layer is, so what happens in this structure is that your current is traveling vertically for the most part. That's not quite true, but for the most part it's traveling vertically. But when you get to the top layer of the top semiconductor, the emitter of the top cell, it now has to turn sideways and make it to one of the grid lines, right? One of the metal grid lines. And you don't want to put those grid lines, you want to find the right place for the grid lines. If you have them too far apart, then you have way too much resistance because of that lateral path. If you put them too close together, you eliminate the resistance, but you also shadow your cell, right? Everywhere where there's metal, you don't get photon absorption underneath it. So you have to pick some optimum. And you'll optimize it for a particular sheet resistance, but then you're stuck with what you have. So as your current turns and travels laterally, you pick up the resistance of the semiconductor. And that's usually the dominant resistance.
Like kind of like a space shard.
It's purely an ohmic resistance at that point. You're now traveling as a majority carrier, and so it's just I²R.
Sorry. I would like to know that how do you tune the current which is generated in each cell? Because the current of all the cells in the multijunction should all of them have the same current. So how do you tune this current?
So like I answered before to this gentleman's question, you have two drivers. You have bandgap, right, and you have thickness. You know, that's to say that you can't change the absorption coefficient. You can change the absorption coefficient a little bit if you dope it. You know, if you really heavily dope it, you'll change that a little. You know, let's leave that.
But you don't know the recombination rate of each layer.
Well, you can. I mean, if you have low recombination, then you can get the maximum. You have two phenomena. You have absorption and you have collection, right?
Yes.
So the absorption is kind of irrelevant to is a separate problem from, you know, recombination, right? The recombination affects the collection. So you absorb a photon, creates an electron hole pair. Now maybe you collect it, maybe you don't. If you have high recombination rates, you're not going to collect it, but you'll absorb it. So you can influence the absorption by changing the thickness. And if you know, ideally you want to choose those band gaps where you can be optically thick.
Okay.
I'm just wondering, what is the chance for materials like graphene to use it like instead of the grading layers, which you use to match the subcells? So what's the chance of graphene to be used in this?
I mean, I don't know really much about graphene. It's probably difficult to integrate into the growth systems that we use. You know, most of these cells are grown by metal-organic vapor phase epitaxy, chemical vapor deposition. And, you know, graphene has a different lattice constants. I don't know a lot about graphene. I'm just guessing that it's crystalline rather than amorphous. And putting that in the same system is going to wreck your material. That's not to say that there may not be other growth systems that are compatible. So you know, that's probably the best I can say, is that it's not easily integratable.
And how do you make sure that the different grading layer that you put are transparent? Because you said you put like 15 to 20 layers.
Yeah. So you choose the band gap. You choose a higher band gap than the material than the photons that are going to be remaining in the structure at that point. And then you make text structures and you measure them. But you know, if you choose something that's, you know, they're heavily doped because you don't want to have resistive loss. But if you pick something that's, you know, several kT above your, you know, your band gap of your filtering layers, then you'll be fine. Judah?
So I know from organic photovoltaics, where you have basically a single bandgap material, that is it is important to choose the right contact metal.
Yes.
With the right work function. Now, how is it here with this multi-bandgap structure? Is it there also an issue, and how do you, or what metal do you choose?
You need to choose you need to choose a good contact. You don't want to have a lot of contact resistance developed. If you have contact resistance, especially at high currents, then it's just another contribution to the resistive losses. That said, it's you know, I think it's been figured out. We use in our lab electroplated gold. We use it for simplicity. It's very fast. It's easy to put down. Most industry does an evaporated contact. They probably do an alloy contact. They probably put down something like, you know, palladium, germanium, gold. You know, a thin layer of palladium, a thin layer of germanium, then gold, and then annealins. You can make very, very low resistance contacts that way. And you also gain from the fact that these the gallium arsenide-like layers can be doped very highly. So you can put down, you know, especially if you're lattice match to gallium arsenide or germanium, you can put down as your final layer, you know, a layer of gallium arsenide. You can dope it to 10 to the 19. There's really no issues of contact here. So,
I'm curious on the figure of the efficiency versus the light intensity. Such in other words, how many cells can reach the best efficiency?
the best efficiencies to date are in the neighborhood of 500 suns. You know, 300, 500, 600. You know, the reason, it's because they're rolling over. So this one is, I'm not sure. Did I understand your question correctly?
No. My question is, do you measure the figures of the efficiency along with the sunlight intensity, such as from the 1 sun to 1,000 or 2,000 suns?
Yeah.
Did you measure this kind of figure?
That's what we're showing you, right? This is efficiency versus concentration. So this is 1 sun, 10 suns, 110,000.
So this depends on the cooling system. Use active cooling system or passive cooling system.
I mean, this is a laboratory measurement, so it's sitting on a thermoelectric stage that's trying to cool it to 25 degrees. This is an indoor measurement under what's called a flash simulator. So you generate this kind of high intensity by taking a discharge lamp and flashing it and collecting all the light onto the cell and measuring your IV curve in 3 milliseconds. So it's not quite the same as outside. Outside you have other problems with the spectrum and with cooling, but
Yeah, so you have a measurement on this graph. So what is the mechanism on the side? Why it increase from the left side and why it decrease on the right side?
So the decrease on the right was what I just answered before, largely driven by resistance. What happens from? That's a great question. And what happens from 1 sun to a higher number of suns is that in general, as you concentrate the light, you get an efficiency boost. And the reason is a little bit technical. Your recombination is given by the diode equation. Okay, so the main driver here is that as you raise the concentration, your open circuit voltage goes up. Okay, as you raise the concentration, your current is going to go up, but it's going to go linearly for the most part with concentration. So those two factors cancel out. But your voltage also goes up. The reason your voltage goes up, your open circuit voltage goes up, is that you have your VOC is created by an equilibrium between absorption and generation. The absorption is going up linearly, but if you look at the diode curve, right, it's an exponential, and if you try to figure out how much regeneration current or how much recombination current you need to exactly balance the absorption, that number increases with voltage. Okay, so at higher concentrations, you need more voltage to develop enough recombination current to exactly balance the absorption. And so your open circuit voltage goes up.
So it sounds like the absorption goes linear, like it goes exponentially with the concentration.
The absorption goes more or less linearly. If you take 10 times the sunlight, you get 10 times the current. But you're going to get a higher voltage.
Okay.
And that's the main driver of the concentration increase. Are you going to add something to that? No, you're stretching your Yes.
What are the degradation happens inside a device structure when it passes to its plant side? And is it possible to recycle this material and reuse these cells again after passing by?
I don't know the answer to the second question. I suspect the answer is no. I mean, there's a lot of dopants. It's just metals. I mean, you have to melt it down and repurify it. And, you should ask the metallurgist, but probably you can.
We are going to preserve these materials plus, so we see our future for 500 years. So all this technology.
These cells are spec to last 25 to 30 years. 500 years. I hope we're still here. I don't. That's a good question. The materials that are being used here are much lower abundance than silicon and carbon, which is part of the reason why marrying them up with a technology that forces them to be small is advantageous, right? The space industry can make flat panels of 3-5 material, and they spend, you spend $500 million on a satellite, you spend, $10 million on the solar cells, but nobody on Earth would do that for a terrestrial market. So you have to use small cells, and that helps to mitigate the material usage. Whether you can reuse them, I don't know. I suspect you probably can. As for the degradation mechanisms, you get electromigration, you get some of the contacts, the metals in the contact, slowly diffusing into the cell, and will be eventually short-circuiting some junctions. You get defects that are created, so there's, for the LED industry, there's a lot of evidence of recombination, current-assisted recombination. So defects start to be created in material, and they get worse when you have a lot of high current flowing through them. You also get hotspots, meaning that the cell is the cell is grown and then it's bonded to what's called a receiver, which is heat sunk, and there's a bunch of contact, and that's put into a system and it's cooled. But if it's not cooled properly, or there's some cracks in the bonding is often the solder. If there's some cracks in the solder, you'll get hotspots, you'll get shunts. So maybe the best way to answer your question is to say that the degradation is probably not at the cell level. The dominant degradation is probably at the module level. Probably, after you take a disputable cell and you give it to somebody else, they mess it up. Yeah.
Yeah, so you're talking about optimizing the metal bridge on the top. What would happen if you used a transparent conductor for the top contact also?
If you had a good transparent conductor, that would be great. There's been some research into that. The best TCOs, I think, have a transparency of about low 90s%. That's not high enough.
Okay.
That's a 7% loss, 8% loss, you're done. So if you can figure out how to make a TCO that has 99.5% transmission and low and good conductivity, you'll be a billionaire.
Okay, do we have more questions? If not, let us thank our speaker for the wonderful. So you probably